Okay, I've been hyping this up for a long time. We've said that Laplace transforms let us get some sort of numerical comparison with how similar our function is with any exponential function, e to the st. We know how to find a Laplace transform. We have a bunch of formulas for different kinds of Laplace transforms. We said Laplace transforms turn derivatives into algebra. We said, what else do we say? We said a lot of things. We said the Laplace transform is linear. Let's actually start using this to solve a differential equation. And we're going to start with a very simple one. Let's go all the way back to chapter 1. Solve the initial value problem. Y dot, or dy dt, or y prime, whatever you want to call it, is y minus 4e to the negative t. So this is a first order linear non-homogeneous differential equation. We can solve this with integrating factors. We can solve the homogeneous version and then find a particular solution and use the linearity principle. We have many ways of doing this, and it's not that hard. We're going to make it a little bit more interesting though. We're really just practicing. I want to practice using the Laplace transform. We're going to use it on more interesting functions eventually, but let's not start with the hard stuff. Let's see proof of concept. Let's see how it works. And it'll be a combination of good news and bad news. So without further ado, we're going to solve it. Actually, before we solve it, let's do some qualitative analysis to see what we might expect. It's always a good habit to get into for solving equations. When we solve an application problem, we have an expectation about how the system should behave. Like, oh, this spring should stop moving eventually, as an exaggerated example. And we can use those like thoughts to kind of check along the way whether our solution's looking good or not. So if we do some qualitative analysis, I didn't give you the initial condition. The initial condition is very important for an initial value problem. We start off at 1. So let's start by doing a little qualitative analysis. What do we expect to happen to the system over time? We don't see any equilibria, right? Because it's not homogeneous. If it were autonomous, then we could find an equilibrium by finding what value of y makes y dot equal 0. I think you're going to have to remember back to one dimension. Okay. So it's not one of those, but we do know that the initial condition is 1, so we do know the initial slope, right? The derivative initially, well, its initial position is 1 minus 4. The initial derivative is negative 1, so we start by decreasing, and we're decreasing pretty fast. And furthermore, as soon as y gets to 0, which it gets to 0 pretty quickly if this is already its slope, as soon as y is 0, y is going to be negative. This is always negative. So the derivative is always going to be negative. So y prime or y dot, however you want to write it, is actually always going to be negative for all time. So you know how this function's going to behave. We know how the solution's going to behave. This solution's just going down, 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 down. Y is going to negative infinity. So we have a qualitative guess about what's happening. We could plop up. We could plot the slope field, right? Graphing our slope field using one of those earlier calculators we used. And we see that there are some initial conditions where it's not decreasing for all time. You can see some initial conditions. If the initial condition's big enough, then the slope has a chance to increase. But our initial condition is at 0, 1. Oh, yeah, we decrease and then keep decreasing faster. So we see that our qualitative analysis was correct. Here, the x-axis is time, and the vertical axis is y. Okay, so let's solve it now that we know what to kind of expect. And we're going to solve it with the Laplace transform. If you want to check your answer, you could solve it using techniques of chapter 1 as well. Okay, so we're going to take the Laplace transform on both sides. So we're going to L both sides. And what that's going to give us is that the Laplace transform being applied to the function y dot, or dy dt, is equal to the Laplace transform of the function y minus 4e to the negative t. And this is, again, going to be a very opportunity to use some nice properties that we know. Okay, and we're going to be using a few formulas here, so make sure that you have this. I will post it in Canvas, but we are going to need this. Ooh, I noticed I didn't actually comment explicitly for constant functions, but we will be dealing with that. Interesting. Okay, so the left-hand side is no problem. We're going to use the theorem to do the left-hand side. And our theorem said that Laplace transform being applied to a derivative, what was it? The Laplace transform of a derivative is S times the Laplace transform of the function minus the initial condition. So this is S times L of y minus our initial condition, which is just 1. I'll write y of 0 to be a little bit more clear. And over here, again, this is a linear operator, so this is just the Laplace transform of y minus 4 times the Laplace transform of the function e to the negative t. Now we see we have some common things we're solving for y, right? We want to know what function does this. So let's move all the y's to one side and all the constants to the other side. This is just a constant right here, right? Specifically this y of 0 is 1. So when we subtract this to both sides, we get the Laplace transform of y times a coefficient of s minus 1. We add 1 to both sides for this guy. We're going to get 1 minus 4. What's the Laplace transform of e to the negative t? We could derive it, or we could just look. The Laplace transform of e to the negative t is just a equals negative 1. And it'll be 1 divided by s plus 1, as long as s is at least negative 1. So I'll have 1 divided by s plus 1, and that's only if s is at least negative 1. So that is a requirement that we're going to need. And we're getting pretty far. We're doing pretty good here. What we have is, again, we're trying to get y by itself. So let's divide by this coefficient. We'll get the Laplace transform of y. If we divide everything by s minus 1, we're going to get, this whole thing divided by s minus 1. And we can split up the numerator. So let's do so. 1 over s minus 1 minus, oh, this was a 4. Sorry. It was 4 times this. Minus 4 over s minus 1 times s plus 1. And again, we're requiring that s is at least negative 1. Any other requirements? Oh, if s is positive 1, we have a big problem as well. All right, so s is not equal to positive 1 either. That's going to be an issue for us. All right, and we have another issue a little bit here. And the other issue is, well, how do we undo the Laplace transform? And it's actually quite easy. And well, it's quite easy, but there's a little bump in the road. You all are going to get a little blast from the past. You're going to see a neighbor that you thought you'd never see again in the next video. But basically, what do is it's like derivatives and integrals. We're now going to find something on the right column and see what it equals in the left column to do that. But before, we'll formally introduce that in the next video with the inverse Laplace transform. But it really is as simple, kind of, as just looking over here, trying to match that up with what we have to find out what y has to be. So to be continued in the next one. Bye-bye.